Hi, my name is Wei Ming, currently a PhD student from the Department of Geography and Institute of Cyber Science at Penn State. Today, my topic is automatic unstructured grid refinement using machine learning for the analog ensemble of numerical weather prediction. Numerical weather prediction models usually use a uniform grid. However, certain physical changes might occur non-uniformly across space and time. For example, temperature might have a higher variability in mountains and lower variability on ocean. It is not necessary to generate a unified resolution predictions across the domain, and when the problem scales up, it becomes even not possible to generate high resolution using a unified grid. So how can we optimize the computation? I approach this question from two aspects. First, how do we generate predictions? And then, where do we generate those predictions? First, let's take a look at how do we generate predictions. I adopted the analog ensemble technique, which generates probabilistic forecast. Figure A shows how it works. It takes a current prediction and it looks through the historical predictions, try to find the most similar past forecast. And then instead of using the predictions themselves, the analog ensemble is going to use the observation associated with the predictions and using the observation to form the probabilistic forecast. Figure C gives you an idea of how the output looks like. Data are collected from North American mesoscale model, and this is a selection of weather variables including temperature, wind speed, V component of wind, vertical velocity. The left panels show the current predictions on January 15th, 2017. And the right panels shows the historical predictions from days in 2016. For example, if we're predicting temperature for 6 in the night on January 15th, analog ensemble is going to look for the most similar past predictions with the highest overall similarity. And then, instead of using the predictions themselves, it takes the actual observed temperature associated with those days and use the observations as our predictions. So then let's take a look at where do I need to generate predictions. I propose this unstructured grid refinement technique. The technique can automatically identify areas with higher variabilities and areas that we need to generate a finer grid. Figure B shows you the steps in the technique. First, I identify unstructured grid topology. To start with, I randomly select a set point in the domain and use them as my vertices to construct triangles. Step 2, I generate predictions only on the vertices, and then I estimate the predictions of each triangle. Triangles will be marked if they have worse predictions, and those triangles will be further refined. This process will loop until we are satisfied with the prediction or we simply used up our computing resources. A final step interpolates the full domain. Using the vertices that we already have predictions. Figure D is a temperature map, and it shows the initialization for the algorithm. Here I randomly select 50 vertices in my domain and construct triangles using the 50 vertices. Here is a video showing how the adaptive unstructured grid grows after each iteration. It is compared with the random grid where triangles are randomly selected and points are randomly added after each iteration. Red dots mark the triangles that need refining. After some iterations, the adaptive grid starts to generate finer grids over areas with higher variability, but the random refinement doesn't show any meaningful trends. Figure F is the result from the unstructured grid using adaptive method. And figure E is the interpolation using the unstructured grid from figure F. As a comparison, figure H is the random grid and the figure G is interpolated from the random grid. It's shown here in the figure F that you can see for the areas with higher temperature variability, the adaptive method tends to generate finer grid. Therefore, in the interpolated map, we have a more detailed information. So how about the computing efficiency and accuracy? Figure I compares the error between adaptive method and random method. Horizontal axis is the number of points that we have computed, and the vertical axis is root mean square error computed between the predicted value and the actual observed value. The green is adaptive method and orange is random method. So adaptive method constantly generates a lower error with the smaller distribution, meaning that it generates a better prediction with higher confidence. Another way to look at this figure is to look at horizontally. To get to the same level of error, we actually need to compute fewer grid using adaptive method and more grid using random refinement. This is essentially what figure J shows you. The horizontal axis is RMSE, which is our error, and the vertical is the speed up rate. If you look from the right to left, and actually we can save more computing resources and achieve a higher speed up rate if we are targeting at a lower prediction error. This work is collaborated with Rutgers University and is funded by an NSF program. Thank you for watching.